Welcome to today's paper reading. Today's paper is titled, Distilling System 2 into System 1. This paper, published on the AR14 preprint, explores the distillation of System 2 techniques into System 1 by Ping Yu and colleagues from Metafair. Large language models, LLMs, utilize additional computational resources during inference to generate intermediate thoughts, which significantly enhances the quality of their final responses. Techniques such as chain of thought, rephrase and respond, and System 2 attention have been proposed to achieve this. In this work, the authors investigate self-supervised methods to compile or distill higher quality outputs from these System 2 techniques back into LLM generations without the need for intermediate reasoning token sequences. This distillation process results in improved performance compared to the original System 1 methods, with reduced inference costs. The authors suggest that System 2 distillation will be a crucial feature for future AI systems, allowing them to concentrate System 2 capabilities on reasoning tasks they currently perform poorly. In this paper, the authors introduce the concept of System 2 reasoning, which involves deliberate and effortful mental activity to avoid errors that might occur with more automatic System 1 thinking. They define System 2 reasoning in the context of AI models and discuss various techniques such as chain of thought and branch-solve-merge. The paper then introduces System 2 distillation, a process where System 2 reasoning is compiled into System 1 models in an unsupervised manner, leading to reduced computational costs while maintaining or even improving the quality of results. Figure 1 provides an overview of the System 2 distillation process. It begins with the collection of filter training examples by employing System 2 approaches, such as branch-solve-merge, BSM, on unlabeled data. These methods utilize additional computational resources to generate higher quality outputs. Subsequently, these high-quality outputs serve as targets for distillation into the standard large language model, LLM, referred to as System 1. This distillation process aims to enhance the performance of the LLM by integrating the reasoning capabilities of System 2 methods into System 1, thereby improving the model's output quality while reducing computational costs. In the related work, the focus is on understanding human reasoning systems and their analogs in neural network models. System 1 in humans is characterized by quick, pattern-based decisions, while System 2 handles complex problem-solving. Similarly, in neural networks, System 1 models output responses directly, whereas System 2 models use intermediate steps for reasoning. The concept of distillation is also explored, where a more powerful teacher model trains a less powerful student model. Recent efforts have aimed to distill System 2 reasoning into System 1 models, though challenges remain, particularly in maintaining performance without intermediate steps. In this section, we discuss the process of distilling System 2 into System 1. System 1 models directly produce output Y from input X, while System 2 models generate intermediate token Z before producing the final output Y. System 2 models can involve multiple prompts and complex processing. The goal of System 2 distillation is to transfer the reasoning capabilities of System 2 models into System 1 models, improving their direct outputs. This is achieved by using unlabeled inputs X to generate responses with a System 2 model, which are then used as targets for fine-tuning a System 1 model. To ensure the quality of these responses, an unsupervised curation step is applied, which includes checking for self-consistency of outputs and consistency under input perturbation. This process results in a synthetic dataset that is used for supervised fine-tuning of the System 1 model, leading to performance gains similar to those of the System 2 model. The experiments utilized the Llama 2-70B chat model as the foundational model, employing various System 2 methods such as Rephrase and Respond, RAR, System 2 attention, S2A, branch-solve-merge, BSM, and chain of thought, COT. For System 1, zero-shot inference is conducted using the instruction-tune-based model. In the Rephrase and Respond method, both one-step and two-step RAR are applied to tasks like the last letter concatenation and coin flip reasoning, showing that distillation significantly enhances accuracy. System 2 attention, S2A, is employed to mitigate reasoning errors, focusing on the sycophancy eval task, where distillation not only maintains performance but also reduces the number of tokens generated. Table 1 presents the results of distilling System 2 reasoning into System 1 for the rephrase and respond method across two tasks: last letter concatenation and coin flip reasoning. The baseline System 1 model, Llama 2-70B chat, shows an accuracy of 30% for the last letter task and 56.1% for the coin flip task. After distillation, the System 1 model achieves a significant improvement, reaching 98% accuracy for the last letter task and 75.69% for the coin flip task. The number of tokens generated is also reduced to 25.5, demonstrating the efficiency of the distilled model. Table 2 presents the distillation performance of System 2 attention on the Trivia Q8 task, focusing on accuracies across biased and unbiased evaluation sets. It compares the baseline System 1 model with the System 2 attention, S2A, and its distilled version, Distill S2A. Notably, the distilled System 2 model shows strong performance similar to the original S2A, but with a significant reduction in the average number of tokens used, which is attributed to the handling of biased inputs by the baseline LLM and the intermediate token generation by S2A. Table 3 presents the evaluation results of the System 2 distillation of branch solve merge (BSM) method on the Open Assistant (OASSD2) and empty bench datasets. The distilled BSM model, based on Llama 2-70B chat, demonstrates superior performance compared to both the original BSM and GPT-4 as a judge. Key improvements include higher human agreement rates, fewer inconsistent predictions, and significantly fewer output tokens required for inference. This indicates that the distilled BSM not only enhances the quality of evaluations but also reduces computational costs. Table 4 presents the accuracy results of the GSM-8K test set, focusing on the number of votes K in majority voting, which indicates the number of candidates sampled to predict answers. Notably, the table highlights that the distillation process of System 2's chain of thought, COT, does not perform effectively in this context. Figure 2 illustrates the agreement levels between large language model, LLM, judges and human preferences across various categories on the empty bench. Notably, the chain of thought, COT, approach enhances agreement in all categories compared to the base model. The distilled BSM model shows superior performance over the standard BSM, although it still falls short in reasoning, coding, and extraction tasks compared to the GPT-4-0125 preview model. However, it excels in writing, math, and STEM categories, surpassing GPT-4-0125 preview. In this work, the authors demonstrated that it is possible to distill System 2 reasoning into the outputs of a large language model, LLM, without intermediate generations, often improving performance. This distillation makes these methods more practical for LLM practitioners and more efficient during inference. However, not all methods can be distilled easily. For instance, chain of thought, COT, remains challenging. Looking ahead, this approach could free up resources to focus on tasks that the LLM cannot yet perform well. Despite these advancements, the effectiveness of these methods can vary depending on the specific task or dataset. The model's performance also relies on the specific filters applied, such as consistency criteria. Alternative strategies to enhance data quality and self-supervised learning were not explored in this research. Thank you for watching.